Okay, it is 1/816. So 91 kilogram refrigerator is placed on a ramp, and the ramp is raised. And when the ramp gets to 34 degrees, suddenly the refrigerator starts to slide down the ramp. You'll be wanting to write this down. So what we want to know is, what's the coefficient of static friction between this refrigerator and this ramp? It's a reasonable question. So we know that when we draw this situation, we've got the refrigerator on the ramp at 34 degrees. We have force of gravity, good old mg. I'll do this in a different color if that's helpful. We have f of gy, f of gx. We have F normal force, Gesundheit. And we have a force of static friction. Where is the force of static friction? So, is it, I'll give you two options. Is this the force of static friction, or is that the force of static friction? Up the ramp or down the ramp? Up the ramp. Force of static friction is up the ramp. Why?
Because it's trying to slow it down.
It's preventing it from sliding backwards. Because remember, friction opposes motion. So if you have a question, look at which way the object is moving. The friction is in the opposite direction because friction opposes motion. Friction opposes motion. Remember, force of friction has oppositional defiant disorder. I don't care where you're moving. No! That's the way it works. So, where is the force that's balancing that force of static friction? The other side. What force is that? It's already on there. FGX. FGX. So, and these are obviously not drawn to scale, but FGX, which we can transpose up there if we want to, is the force that's actually going to end up moving that refrigerator down the ramp. And I'll move that back to the bottom because I get confused otherwise because, you know, little pea brain these days. Okay. And I tried to draw force of static friction to a better scale with force of gravity on the x. What we want to know is the coefficient of static friction. So I'm going to start out by writing the equation for the coefficient of static friction. And looking at what I need. So I need to have normal force. I need to have the force of static friction max. Neither of those things are given me in the problem. So what I have to do, remember how I've been saying for the last two chunks, start with the sum of forces, start with the sum of forces, start with the sum of forces. Sometimes even if you don't need it, you should start with the sum of forces. Guess what we're going to do here? Sum of forces. So we can say, well, let's look at the sum of forces on the y-axis. Is this thing rising into the air or sinking? No. What's the sum of forces on the y equal to? Zero. It's at equilibrium on that axis. It's all the forces up plus all the forces down. What forces up are acting on this object? Normal. What's the force down? Force of gravity, which? On the y. Because remember, we split force of gravity. So therefore, what we find is that Fn equals negative f of gy. Fn, we can write an expression for f of gy, which is fg cosine 34, cosine theta. And of course, that's Fn equals the negative of mass gravity cosine 34. Okay, so we now have this, which we can plug in right there. That's convenient. going to shrink a few things. So now we have to work on some way to get an expression for force of static friction max. So let's look at the x-axis, because that's where the force of static friction is going to exist. On the x-axis, what we know is that at the moment that the thing starts to move, so we're going to write at movement, because we want to remind ourselves that this is at one specific moment in time. At the moment in time when the object starts to move, the applied force must be equal to what? Maximum force of static friction max. So at the moment when it breaks loose and you feel it start to move, that is the moment where the applied force has become equal to the maximum possible force of static friction. It's this instant in time. So we're not even going to say that this is equilibrium, but we know that at that moment, Fs max equals f of gx. Well, equals negative f of gx. Sorry, they're equal and opposite because they're over. One has overcome. So force of static friction max then is equal to the negative mg. Fgx is opposite the angle sine of 34 degrees. Okay. So now we have our second piece to plug in there. So the new equation that we're going to write is going to look like this. Mu s equals negative of mg sine of 34 divided by negative of mg cosine 34. Let me ask you a question. Could you solve this problem if you didn't know how much the refrigerator weighed? Yeah. Because what happens to your mass gravity here? Cancels out. Disappears. Yep. So in this case, mu s ends up being equal to the tangent of 34. So we get a mu s of, well, if we're using the 34 and 91, yeah, it'd be 2 sig figs. So 0.67. Yep.
That's fancy.
Isn't that fancy?
With no units.
No units, because it's a ratio. It's a unitless ratio. I know. It gives me hives to not write down units.
This is like giving my brain a break.
Huh?
This is like giving my brain a break from the other force question.
Oh, don't.
Please, just let it be.
Okay.
Just where it is.
Okay. All right. Sure. So let's do one more that's another one that has some complications. The big thing I wanted you to see here is how you can start with really very little information. You have a mass and an angle. And can you figure out the coefficient of friction? You can. And if you weren't given the mass, you could still figure it out. But the big thing that I want you to see and think about and get accustomed to is this. Again, I keep stressing it because this is only an Algebra 2 course if you let it be an Algebra 2 course. In Algebra 1, you would have solved for a bunch of numbers and written them all down and plugged them back in. In Algebra 2, you create expressions and you substitute expressions back in, and then you perform further algebraic maneuvers on that larger equation. So that's where you build the skill. Creating expressions and subbing them in is really something that picks up a lot of steam here, because we suddenly have 2 more things from which we can build expressions. We have the coefficients of static and kinetic friction, which gives us relationships between normal force and the force of friction, static or kinetic. Because of that, we suddenly have a whole lot more ammunition to build expressions with. Okay? So let's do one more weird one together. A box slides down a 30-degree ramp with an acceleration of 1.20 meters per second. Determine the coefficient of kinetic friction between the box and the ramp. Oh. Okay, so draw it. So thus far we have what? Force of gravity, F of G on the Y, F of G on the X. What other forces do we have? Normal.
Oh my gosh.
Okay, so we've got normal force. And what other forces do we have? Force of kinetic friction. In which direction is that going? Up or down the ramp? Up the ramp. So we have F sub K. Now, and I did not draw that one to scale yet. Again, let me fix that. So, this is a pretty picture because we don't have an equilibrium situation here. We have something that's accelerating. So let's deal, first of all, so we're finding the coefficient of kinetic friction. So let's write down the equation for the coefficient of kinetic friction so that we have that. So we know that mu k equals Fk over Fn. Okay. Now, of course, we have neither Fk nor Fn, so it's up to us to figure those out. Fn is definitely the easier one to do here. Why? Because the y-axis is equilibrium. So we can see automatically if this thing is not rising into the air or sinking through the ground that Fn is going to equal the negative of Fgy. But you still got to write an expression for it. So negative of Fgy equals Fn, or negative of Fg, and looking at that angle, it's going to be cosine theta equals Fn, and you can go one more and say, well, negative mg cosine theta equals Fn. You know, and another good reason for creating all those expressions and not solving, in the last problem, if we had done just mass gravity would have still canceled, but anyway. Okay, so we have an expression for Fn, which of course we'll use there. The expression for Fk is going to be a little bit more complicated because we're not at equilibrium. So again, you do have to shrink that. You do have to write the expression. So sum of forces on the x is equal to mass times acceleration, which is also equal to force of kinetic friction plus what? Yep, Fgx. So if we just want Fk, ma minus Fgx equals Fk. So ma minus mg, and in this case it's sine theta, equals Fk. We could factor out a mass if we wanted to. But what we have now, oh, I'm sorry, make that a negative. No, it's not. Okay. So what we now have is an expression that we can put in for Fk. So let me shrink all of this, and we'll put in our substitutions. Mu k equals ma minus mg sine theta over the negative of mg cosine theta. Now, if we didn't know the mass of the box, oh wait, we don't. Does it matter? Nope. because the ratio, this is a ratio. So whether we have a 10 kilogram box or a 100 kilogram box, the coefficient of static friction, the ratio between the forces of friction and, or not static, kinetic, the force of friction and the normal force is going to be the same ratio. It's a ratio relationship. So we can factor out an m, mu k equals. So we factor out an m, we have a minus g sine theta, negative mg cosine theta. We can get rid of our m's. Mu k equals a minus g sine theta over g cosine theta. So we're now ready to plug in numbers. So we've got mu k equals 1.20 meters per second squared minus negative 9.81 meters per second squared times sine of 30 over the negative of negative 9.81 meters per second squared times cosine of 30. Okay, so who here is getting 0.647 something? Okay. Who here's getting something else? Anybody getting 0.436? Okay. What did you do algebraically differently than what I did? So the book says 0.436. I've done something wrong. Where's my mistake? It's a treasure hunt. Yeah?
Could you cancel out that number and negative then?
Take
The-
out negative n.
Hmm?
In the, when you originally took out the n, did you take out a negative n? Or did you take out a negative?
No, well, the negative, you mean here?
No, I'm talking about the original equation before you took the n out.
Here.
Yeah. So it would change that sign to positive.
Well, and that would have you adding the 1 point, that would have you subtracting the 1.2 and the, so you're saying if this was addition, not subtraction, in essence. Is that what you did?
No, I took 1.0 minus the gravity sign.
Instead of adding them. Interesting, because, let's see, okay, let's think this through. This is where, when I talked about like really fighting with these problems and fighting with the sign, so let's think about it in these terms, and let's enlarge this. Okay, so the force of kinetic friction overall has to be a positive number. The force of kinetic friction, if it's moving down the ramp, no, I actually think the book might be wrong. Because okay, so let's think about this conceptually. And remember, I have already found one error that they've admitted to in the subsequent edition to this book. The force, if this thing is accelerating down the ramp, in which direction is the force greater? Up the ramp or down the ramp? Down the ramp. So just if it was staying still, the force up would be equal to gravity. So let's look at this conceptually like this. So if this object is sitting there not moving, and this is our force of gravity on the x, and this is our force of friction, this would be static, it's not moving. These two have to be equal. If this thing is accelerating down the ramp, then you've got to not only overcome gravity, you have to have a force on top of that. So this has to be an addition of the addition. It has to be additive. It can't be subtractive. So I think the book has an algebra error. I'm going to argue that one, that I'm right and the book's wrong. The force down slope has got to be greater than gravity, so it cannot be less than gravity. So force of kinetic friction, oh wait, no, I'm arguing against myself. So force of kinetic friction has to be less than the force on the X, which means that, okay, hold on, let's go back to this. So this is force of kinetic friction is what we're saying. We are saying then that the acceleration downslope minus whatever force of gravity is there has to yield a smaller force than the force down the slope. Okay. We're going to pick this up on Monday. What I'm going to do is give you a 4C worksheet before you walk out. So pick up one of these, and we'll continue to fight with these problems. They do turn into a real sort of knockdown, drag out, I'm afraid. So start with the odds on 4C.